Hello and welcome to my Lab 1 submission video about constant velocity. First, let's go over some introductory and background information. We have Newton's first law, which is inertia. We have Newton's second law, which is the momentum principle. And we have constant velocity, which means there's a zero net force acting upon the object. However, this does not mean that the object is stationary. It can, of course, also be moving. Some important equations that can be derived from Newton's laws include the updated position formula and the updated velocity formula. In the velocity formula, you can see that if F net is equal to 0, then the final velocity is equal to the initial velocity, making it constant. So today we're going to be experimenting with some of these ideas and the resulting relationship between position and time. So first, we're going to observe an object in motion with constant velocity using tracker. I decided to use an orange. Then we're going to create a computational model of this orange moving using GlowScript. Next, we're going to create a graph plotting both observed and predicted position versus time coordinates of said orange and compare the results. Lastly, we'll answer some additional questions and conclude the lab. We have some observations from Tracker here. I imported the video of the orange moving across the table. And using Tracker, I was able to collect data needed for the computational model. This includes the start and end time, the initial position, the initial velocity, and the coordinates of position versus time. Here is the computational model from GlowScript. I used a starter code and then inputted the data I collected from the Tracker observational model. This includes the mass, the initial position, the initial velocity, the time, the end time, the force net equaling 0, and of course the updated velocity and position equations. And when we actually run this code, it looks like this. There it goes, my orange moving in the positive x direction, because that's where we put the coordinate axis in Tracker. Our position versus time graph has a positive slope. Our velocity versus time graph has a constant straight line. It's constant. And then, of course, we have the coordinates of position and time. So now that we have both coordinates from Tracker and GlowScript, we can create this graph, plotting both of them on the same plane for easy comparison. As you can see, the red line, the predicted motion, is completely linear. It's perfectly straight with constant velocity. The blue line, the observed model, is slightly off, but this can be attributed to friction and the non-perfectly circular shape of the orange. Some improvements that can be made next time this experiment is replicated were to cut the video before the speed changes towards the end. What if I decided to change where the origin of my coordinate plane was so that the orange was moving in the negative x direction? Well, the position versus time graph would look like the graph on the bottom with the blue line. It would have a negative slope and it would be going, it would be reflected across the x-axis. The observed velocity, however, would stay the same because it doesn't matter what direction the object is going in, it still has the same speed. What does this all mean? Can we ever know the exact number of forces added up to create a zero net force? Since we used Newton's second law, there is no way to determine exactly or how much each force plays a part, but we can make a general statement and say that friction and momentum played some role. In conclusion, Newton's first and second laws help us observe and explain why objects move the way they do. Computational models and computers are an extremely powerful tool that can do all the hard and tedious calculations that we don't want to. And the differences between observed and predicted motion can be chalked up to human error and outside forces. Thank you all for watching.